if you 0 by 0 is 100%. Just as in this case, it's indeterminate form. You if to compute the F score, you assume it's 1. So if you just to explain to the rest of the class, the F1 score is the harmonic mean of precision and recall. And precision is, let's say it's defined for a particular label. Let's say for the label true or label false. So let's say for the label true, you measure how many times did your classifier predict true, and of those predictions, how many of them were correct. So that ratio is precision. Recall is how many trues were there in the original test set and how many did your classifier discover. So the only thing that changes between precision and recall is the denominator. In both cases, the numerator is the number of times you're predicting true and it's correct. For precision, the denominator is the total number of truths that you predicted. For recall, the denominator is the total number of truths that exist. How many truths did you recollect? Was your classifier able to recall? Sometimes it's possible that the precision might be you did not predict a single truth. So the denominator is 0. Of those 0 truths that you predicted, how many were correct? 0. So you get the precision is 0 divided by 0. And for convenience, you assume it's 100%. All the truths that you predicted were correct. You did not predict any of them, but all of them that you predict were correct. And so the recall, so it's a classifier, if you want to get 100% precision, you just predict false all the time. So your recall on the precision on that label true is 100%. If you want a classifier that gets 100% recall, what you do is you predict true all the time. How many truths did you discover? You discovered all of them because you predicted only true. Yeah, sure, you predicted a lot more truths, but you're not evaluating that. It's trivial to get 100% precision and recall, but that's really not the job that we have. Yes?
But so I guess even though one of them is when it ends up evening out because it has two factors that are multiplied.
Right, that's why you measure the F1.
Oh, okay.
The F1 is the harmonic mean of these two things, so you need to do both of them well to actually gain points on the F score. And in your homework as well, you're measuring the F score right now. So, yes?
I understand that there is an inverse relationship between precision and recall. But is it so possible that my precision is 80% and recall is 70%?
Yeah, that's entirely possible. There's no formal inverse relationship. Typically, the precision recall curve, if you are willing to live with a blue screen, I can draw on this. The precision recall curve might look like something like this. If your precision and recall, your class, it may not be inverse of each other, but there might be a drop off when one increases, the other decreases. And sometimes the game is to find a point where they are equal.
How compared to algorithms, precision and recall for both algorithms?
What do you mean? So
I just heard that like your precision increase, your recall might drop.
Right.
Like,
so you can trivially increase the precision or recall by changing the threshold. Right? If you have a classifier and you change the bias value, if you increase the bias value, then you predict fewer and fewer true. If you decrease the bias value, you predict true more and more. So after the training is done, this is like a thing that knob that you can tweak to change control precision recall. Right, let me make one more attempt at fixing this.
Oh, should be.
Try the connection between the adapter and
I got up a page where about the question.
Try the this one?
yeah, I don't know.
Supposed to be double
Yeah, yeah, I know. There are only 4 failure points here.
Probably means
That's
we'll
out.
go over. So, but that's fine.
So, how many people are incredibly bothered by blue?
The blue makes it really hard to read.
Okay,
Pink
let's see if
is,
we can get another color today.
pink is best.
That works.
Okay, so pink slides today. All right, so intermediate reports due today. You need to tell me what your evaluation is, how you are evaluating your classifier, and in an ideal world, you should also have some sort of baseline system ready. What's a baseline system? A baseline system is sort of a simplest idea that you can try to solve the problem. One example of a baseline system is you find the majority label, the label that has the most frequent label. Let's say in your data set, there are 80 trues and 100 falses, and you predict true all the time. The classifier gets 80%, right? So, or if you, for example, there are 55 trues and, oh, you're back. Can you throw that at me? I don't think it's the problem with that. I think it's the cable. If anyone else has a cable that connects these. Won't work.
Is it not a VGA?
The other end is not right. That's fine.
VGA.
VGA.
Just like it. Or if one of my TAs, if anyone sitting at the back, could get me a cable, the VGA to VGA cable. Got one here. No, you probably need to go. From Chris Coleman, the front office. Actually, hold on. Okay, this is interesting. I think. Wow.
I've got other cables in there too.
Why do you have that in your backpack? Never know.
No. That's the TH tab. That's the camera back.
Okay, while I'm doing this, I'd also like to talk about the project. So, are there any other questions about the intermediate report? So, you need to tell me what your baselines are. You need to tell me why the baseline is meaningful. Baselines should not take a lot of time. These are like the simplest classifiers that you should be able to come up with. In an ideal world, you should not. So, for example, think of what you would do if you did not know about machine learning. That's a good baseline. A heuristic, for example, something like a rule-based system. That's a good baseline. Another baseline is, let's say you want to try like a really complicated classifier. Let's say you want to try boosted decision trees for your project. A good baseline would be something like perceptron, because basically something simpler than the most complicated thing that you're going to try. Oh, cool. Awesome. Thanks, Jay. So there's some value in carrying around a big cable. Okay, are there any other questions about the project, intermediate reports? And for those of you who are doing the competitive project, remember that the contract that you agreed to is that you would run you try out two classifiers before the intermediate reports due. So you should tell me what classifiers you did, how they performed. On the development set, hopefully you uploaded it to Kaggle, and you should tell me what Kaggle reports. Please make your intermediate report no more than 2 pages, and please do not try any typographic tricks. Font size 6 is not fun to read, so just be reasonable. Yes.
And in terms of the pointers to literature, what are you?
Oh, right. So pointers to literature is just if you have read any papers around this. So some of you are actually trying out projects that require some papers to be read. So if you've read any papers about this, if you've read anything about this, so let me know. Because think of your intermediate report as the scaffolding for your final report. This final report will be an intermediate report grown to 6 pages. So the part of the reason why I'm forcing you to do this now is so that you kind of have some, it's an exercise to force you to get started with your final report, which is due in about, a month. So it's just to get started. Alright, I think I've spent enough time on this. Are there any other questions or any concerns about this?
The literature doesn't need to be like official research papers, right? It could be like online tutorials or
For now, yes. For the final report, you should probably kind of synthesize those tutorials into a background section. For now, yes, that's fine. Alright, so I think now that we're done with that, we can go to the curse of the kernels. Actually, kernels are fun. Just to remind you where we are, in the last class, I was not here, but Xingguang tells me that he talks about the stochastic gradient descent algorithm for support vector machines. Just to remind you what SVMs are, support vector machines are a way of training a linear classifier where you basically look at learning as minimizing a certain objective function. And we looked at how this objective function is derived. Essentially, there are two components. There is one side of the thing that says you minimize half of the norm of the weight vector, which essentially is a way of saying maximize the margin. So the first term, that's called the regularizer, is a way of controlling the capacity of the linear classifier. It's a way of saying that I prefer simpler hypotheses, and the way you do that is by maximizing margin. And maximizing margin is, you can prove that it's equivalent to minimizing the norm of the weight vector. That's the first term. The second term here is the sum of the slacks. Basically, your data set might not be linearly separable, so you allow the learning algorithm to decide I'm going to ignore certain examples in computing the margin. But you want to penalize the learning algorithm if it ignores too many examples, because in the limit it can technically ignore all examples and just find the zero weight vector. So the second term says you're allowed to ignore examples, but here's the penalty you pay if you allow examples to violate the margin condition. So you have these two terms, and there's a trade-off parameter C that lets you trade off between these two. The first term is, you can think of it as a way of pushing for generalization. The first term says I want to favor hypotheses that generalize better. The second term, the sum of the size, says I want to find hypotheses that fit the training set better. So you're trading off between overfitting and underfitting. And there's this one knob that controls how much overfitting or underfitting you like, and that's this number C. If C is higher, you get more overfitting. If C is lower, you get less overfitting. And we saw how we can eliminate all these things and just get a single line object is slightly more interpretable. The way to interpret this is, again, the first term is still maximize the margin. The second term is a sum of losses, sum of penalties. Let's say an example xi with label yi is correctly classified, and the score yw transpose x for that example is out more than that example is placed outside the margin. So you have, remember that you have the hyperplane and then you have margin on both sides, and if the example lies here, and let's say this side is positive, if the example lies here, then the penalty for that example is 0. That means yi w transpose xi is greater than or equal to 1. Then the penalty is 0. The second option is the example is correctly classified. It's between 0 and 1. The example is correctly classified, but it's inside the margin. So what's the penalty? The penalty is the difference between one. How much has it violated the margin? And ideally, we want to find weight vectors that minimize that. The third case is a mistake. The mistake is when the example is here and it's a label plus. Was there a question? Yes.
What is the range of C?
What's the range of C? C technically is any positive number. It's between 0 and infinity. Let's actually think about what happens when C is 0 and what happens when C is infinity. If C is 0, that means this entire term disappears. What you're doing is you're taking the training set, throwing it out, finding a weight vector that minimizes the norm of W transpose W. What is the minimum value of W transpose W? So you have a vector. What is the smallest length of that vector?
0.
0. So the minimum norm of a vector is 0. So what will happen is, and which vector has that smallest length? What's the value of W such that W transpose W is 0? 0. So what will happen here is if C is infinite, if C is equal to 0, the optimization will converge upon the 0 vector. I got one, thanks. Thanks for the trip. Yes.
Have you changed the SVM lectures?
We were before.
Okay,
This slide is one of the earlier slides that existed.
okay.
This is slide 31. Okay, in the original set.
So if C is equal to 0, then the optimization will converge on the 0 vector. The 0 vector is fantastic because it has excellent generalization. Why? Because remember it has essentially, it's the same as saying your margin is infinite. Infinite margin is very good. Actually not quite, because beyond a certain limit the VC dimension changes. But anyways, see, the weight vector being 0 has the maximum margin possible, but that's the good news. The bad news is you completely ignore the training set and you have a weight vector that is overgeneral. So this is the curse of overgeneralization. So C equals 0 corresponds to overgeneralization. Let's take C equals infinity. When C equals infinity, what you do is you're minimizing this quantity, right? When you're minimizing the quantity, if C equals infinity, that means the only way to minimize this quantity is to make the thing inside the circle 0. Right? The only way to have a real valued answer to this minimization problem is if the thing inside the circle is 0, because 0 times infinity is the only possible value way to get a real number. Otherwise, any other non-zero number times infinity is infinity. So what the optimization will do is, as C gets higher and higher, it tries to overfit the data. It tries to find a value for the W and the psi, the W, such that every training example is on the correct side of the margin. So that's not good, because sometimes your data might not be separable. But even worse, your data might be separable, but it might have noise. So maybe it might be in your best interest to actually ignore some examples. So in this formulation, C equals 0 corresponds to underfitting or overgeneralization. C equals infinity corresponds to overfitting. Both of them are not good, so that's why you need to find a good C by cross-validation. Alright, so just to quickly conclude this the review, you have 3 possible values of this, and what is interesting is the thing inside the box here, this penalty term here, is a loss function. It's probably maybe your first loss function that you've seen in the class so far. It's a loss function that you want to minimize. Actually, it's a second loss function because you've already seen the squared loss when we were talking about least squares regression. This is called the hinge loss function, because if you plot it as a function of y w transpose x, it looks like a hinge. And it's 0 here. This is the hinge loss function, and one way of interpreting the support vector machine is that you are minimizing the regularized hinge loss. Now, you're not just minimizing the hinge loss, you're minimizing the hinge loss plus a regularizer. So, the support vector machine is a regularized hinge loss minimization. So, it's nice to write down an optimization problem, but how do we solve it? And this is what Chingwen covered in the last class, where you guys saw stochastic subgradient descent for support vector machines. I'm not going to cover this again, but just to give you a flavor of the algorithm, it looks a lot like the perceptron algorithm actually. You have multiple epochs over the training set. In each epoch, you first shuffle the training set, and then you iterate through the entire set of examples. What do you do? At each step, for each training example, you take a step in the subgradient direction, in the negative subgradient of the objective. But what it means is, you take a training example, you pretend that this training example is your entire training set, you write down the SVM objective, which is the regularizer plus hinge loss for that example, you compute its derivative, and take a step in the opposite direction of the derivative. You can compute the derivative for the SVM on paper, and I hope you have seen that. What that means is that once you take the derivative and you actually implement it in an algorithm, it ends up looking like this. There are two parts. If suppose you compute, for using the current value of the weight vector, you compute the value of the dot product of w and x, and if y times w transpose x is less than 1, namely if that example is either incorrectly classified or if it's correctly classified but on the wrong side of the margin, then you need to make an update. What do you need to do? Let's first ignore this part here. The update, let's just ignore this part here. Update must look a lot like the perceptron algorithm. W is W plus something that looks like a learning rate times Y times the X. But does that make sense? So it looks a lot like the perceptron, except in addition to that step, you also shrink the W. You shrink the W because gamma is a number between 0 and 1, which means W becomes some smaller version of W plus a step. You shrink the W. Why do you want to shrink the W? Because shrinking the W lowers the value of this term here. So shrinking the W gives you a better margin. Yes?
So 1 minus gamma is the forgetting rate.
Yes, you forget what you saw before. Slightly. So that is if you have either made a mistake or if your classifier predicts, if the score for that example is on the correct side of the hyperplane but within the margin. Because being within the margin is a bad thing. So that's the if part. Otherwise, what you do is, you've not made a mistake. What does perceptron do if you don't make a mistake? Nothing. You just carry on. The support vector machine, what you do is, if you make a mistake, you still make an update. If you made a mistake, then you try to gain some margin points. What you do is, the weight vector has not made a mistake, you try to make the margin slightly wider, and hopefully that still does not make a mistake. How do you make the margin wider? By making the W smaller. How do you make the W smaller? By multiplying by a number between 0 and 1. This is again called shrinking. So you shrink the W's if you've not made a mistake. That way so you can think of this as a game. You try to gain points by making the W smaller or by making the loss smaller. And in all cases, you try to make the W smaller, this part, by shrinking, and you make the loss smaller by taking this step here. Questions about this? About the idea of about stochastic subgradient descent? Yes.
Where does gamma come from? Is that just a hyperparameter?
Gamma is a learning rate. Gamma is it's like the hyperparameter, and there is a whole set of tweaks and games to be played with choosing a good gamma. I think one of the slides that you saw last week had an example of one value of gamma. If you're interested in, so stochastic subgradient descent is getting it to work, requires some amount of playing around with the code. There's an excellent paper called Stochastic Subgradient Descent Tricks, which summarizes a whole bunch of folk knowledge on these things. One example for choosing gamma is, this is some t, right? So, in fact, here I have gamma t, right? And one way of t changes every time you see an example. So t, initially you set t equals 0 here, and you increase t here. So every time you see an example, you increase t, or actually you set t to, let's say you set t to 0. The previous lecture had an example of how to choose gamma. A simple thing that works is 1 over 1 plus t, something like this. Basically, all you need is a decreasing schedule. of learning rates. And it has to decrease in a certain way. The convergence proof requires that the gammas add up to infinity if you let it run forever, but if you square the gammas, that should not be infinite. So it is not summable, but square summable. So, yes.
So this convergence is for a stochastic gradient descent, because
Yes.
the other one has to converge. A gradient
But-
descent.
Almost, that's right. Again, you need some, if your learning rate is too big there, the gradient descent, then you'll be bouncing around. So, in general, these days, I end up using gamma to be this value, and it seems to work. Yes,
So do we have to shrink the W every time?
that's right. You have to shrink the W every time, and in fact, there's a nice little programming optimization that you have there, where you, irrespective of whether the YW transpose X is less than 1 or not, you shrink the W, and then if it's less than 1, you add something to it. Yes.
So there's another formula on the slides for the.
Yeah, there's another one as well. That also
So
works.
these two can be they can both be used.
They can both be used, and there's a whole bunch of other things that can be used. So,
Is that another one? Should we also try that one?
sure, right.
Okay.
I have not found a difference, to be honest.
Oh.
So, if you can find a difference, let us know. I'm curious. Yes.
For this organization problem, does it have the only solution for the, have another solution for it?
No. So this is convex.
Yeah,
Because it's convex, it has a unique minimum,
yeah.
which means there's only one solution, and this algorithm will find it.
I think it's another method like the semi-dependent.
Yeah, they'll all find the same object, the optimum. The difference is how fast you get there. The
That's your proposal, this is subgradient method.
Actually convenient because of two reasons. One, they are easy to teach. I don't have to teach you optimization. I can just write down an algorithm and everyone can implement it. And two, subgradient methods are actually have become the de facto standard for developing learning algorithms these days. If you look at all the deep learning literature, most of them end up implementing some sort of a subgradient. So you write down an objective function of this kind, and you compute the gradient and the subgradient, and you just go on. How do you compute the subgradient? And there's a very famous algorithm for that. It's called backpropagation. So backpropagation is a computational way of just calculating the gradient. You remember how we tried to calculate the gradient on paper, and it kind of tends to be kind of irritating, especially if your loss function gets tedious. You can, with backpropagation and stochastic gradient descent, you can basically turn learning into a factory, where you just write down objective functions and give it to this factory that spits out a learning algorithm. So it's very convenient. So the creative part is not in defining hypothesis spaces and not in defining learning algorithms, but the creative part now becomes defining the objective functions. All right, my introduction took about 15-20 minutes longer than it should have, because let's now get to the actual content of the class. We're going to talk about support vectors and duals and the idea of kernels. So it's going to be slightly, somewhat different thing from what we've seen so far, and those of you who recognize this sentence, good for you. What we have seen so far is support vector machines and the idea of hinge laws. But I want you to remember that all of these things are just linear classifiers. You get some space, you cut the space into two, and you get one. You call one side positive and the other side negative. And the way you cut the space into two is using a line or a hyperplane. The natural question is, okay, so how do I use all this technology to build nonlinear models? And we've already seen one way of doing that. One way of building nonlinear models is to explicitly introduce nonlinearity by blowing up the feature space, by transforming the features. So if you want to separate the squares from the circles, and it's clearly not linearly separable, let's say it's quadratic, you can transform all the input points to this new feature space, which consists of linear terms and quadratic terms. What this means is, if you eventually learn a classifier on this new space, phi, get the separating hyperplane will look something like, let's say there's also a bias. So W0 plus W1 x1 plus W2 x2 plus W3 x1 square plus W4. The predictor looks like this, right? It's linear in the new space. It's linear in the new space means it's quadratic in the original space, and thus we have introduced a non-linearity in the original space. And you should be comfortable with this idea of feature transformations. Make sense? And we call these feature functions phi. I mean, typically we'll be using the symbol phi to denote functions that compute feature functions, compute feature vectors. Okay. So we can try to find, once you've done this transformation explicitly, you can give it to any algorithm that learns a linear classifier, give it to perceptron or Winnow, or actually balanced Winnow, or support vector machines, you'll get a quadratic classifier. But SVMs have an interesting property which actually lets you do this slightly more efficiently. I'm not going to tell you about the algorithm for doing this efficiently. I'm going to give you the mathematical basis and introduce you to the idea of kernels. Unfortunately, I am not sure if all of you have taken a class in optimization, so I don't want to get into the details of convex optimization. So I'm going to try to skirt around optimization. But just as a pointer, one way to kind of immediately increase your machine learning skills is to take a class or read a book on optimization, because these days machine learning is largely being treated as an application of optimization, of mathematical optimization. So, for example, an example of an optimization problem is this SVM objective. You want to find a weight vector that maximizes the margin and that simultaneously minimizes the regularizer plus the loss. This form of an objective is called the primal form, and there's a reason for calling this primal. It turns out this is equivalent to another optimization problem called the dual. And the dual has an interesting property. The dual is just another optimization problem. So what are the variables in the optimization problem here? It's the W and the Xi, right? So by solving this optimization problem, you'll get a W and you'll get a Xi. You'll get the best W's and X's. The dual problem is another problem that is intimately related to this same. Every primal problem has a dual problem, which is in a completely different space. So you minimize. So just like you're minimizing over W primal, gives you W star, the best one. The dual will be on a completely different set of variables. It's a maximization problem over a new set of variables. We'll call them alpha, and that is the best value of dual. Let's call that alpha star. Now, it's just another problem. What is interesting about the dual problem is it's set up in such a way that the best alpha. This is the R max. The minimum value of the primal, not the minimum, not the argmin, but the actual minimum value of the primal is equal to the maximum value of the dual. So the dual is, so in primals you're trying to go down a curve, and you're trying to get to the minimum. So you're trying to go down this sort of curve. This is the primal going down. The dual might look something like this. You're climbing a hill, and these 2 points are the same. The height of the maximum height of the dual is the minimum depth of the primal. So for every primal problem, you can convert it to a dual, and there are standard ways of doing that. But what is interesting is, so remember, the main thing that you have to carry from this is the dual problem. There is a dual problem for the support vector machine, and for now, let's call the dual variables the alphas. It turns out that if you minimize the primal SVM problem, you get a W. Let's say you minimize the problem for some particular data set with M examples, and these examples are Xi, Yi. Let's say the W is the best weight vector. Turns out there are alphas which are positive, and you assign one alpha for each training example. And what is interesting is that the W that optimizes the SVM problem is simply a linear combination of the yi times xi. The weight vector is just a linear combination of the input points. A linear combination how? Every point is scaled by alpha. So if you have 3 points, so let's say you have x1, y1, x2, y2, x3, y3, then at convergence, and only at convergence, the best weight vector for SVM will be equal to sum alpha 1 times y1 x1 plus alpha 2 times. It's just this linear combination of the training examples. Does that make sense? I mean, the reason I spoke about primals and duals is that if you care about proving this property, you have to go through the primal dual formulation. It turns out these alphas are the dual problems variables, but you don't need to worry about that. If you didn't get that conversation, you can. All you need to know is there exists such a thing. But what you need to know is that the weight vector at convergence for the SVM will be equal to some linear combination of the training examples, which is pretty cool, right? I mean, it seems very neat. I don't know about you, but to me this seems like a completely unintuitive result. Are there questions about this? So let's see what this means really. Let me just erase this. Before we go ahead, are there questions about this statement? Yes.
So is the alpha here, is it the same alpha as you were talking about in the previous slide
Yes.
with the dual form?
Yes.
Okay.
The alphas are the dual variables. The alphas are the dual, the variables that were used to construct the dual. Yes.
And alpha sub I would be 0, kind of is similar to thinking about we're going to ignore this example.
That's exactly right. We'll see in the next slide maybe or not, but this is exactly right. If alpha I is 0, what that means is that that point is irrelevant for the weight vector. What does it mean to say that that point is irrelevant to the weight vector? It turns out actually we can make a stronger statement than what you said. Not only is that point irrelevant for that weight vector, if alpha sub I is 0, that means for that particular example, y w transpose xi will be more than 1. So alpha I will be 0 for all examples in the training set that are on the correct side of the margin and outside the margin. Okay? So alpha I is a way of, alpha I equals 0 means those examples are correctly classified. Yes?
Why are they 0 again? I mean,
No, they can be 0, right?
yeah, they can be.
Yeah, so I'm just interpreting I'm just giving you, at this point, I'm giving you statements, think of these as just facts.
Okay.
If you want to prove it, then you have to basically, these conditions are, they come from what are called the KKT conditions for optimization. The Karash-Kuntaka, if you have seen it.
So,
Yes. You have a, first you, then you. Yes.
so the only alphas that are relevant are the support vectors.
We haven't, yes, that's right. So, I'm coming to that. You had a question?
I'm trying to understand that because that seems the opposite of what I would, like, in the previous problem we were explicitly ignoring the points that were inside the margin.
You were ignoring the points inside the margin in order to define the margin. But if you are talking about which points you are actually ignoring, those are the ones that are used to define the W. Intuitively, what this means is, imagine there's a hyperplane here and there's a point that's far, far away. It should not influence the position. Changing that point slightly should absolutely not change the hyperplane. But if there's a point that's very close to the hyperplane, let's say it's this one here, or actually not close, but inside the margin, changing the point slightly might actually change the definition of the plane. So in fact, I can even go further than that. If the value of alpha is equal to c, that means this point is on the wrong side of the margin. So I think I might have put the I put the, I'm not sure if the picture is correct, but alpha equals c means these points are either misclassified or are inside the margin. So alpha will be equal to c for all those points that are on the incorrect side. And some alpha will be some value between 0 and c. By the way, this c is the same c that you had in your SKM objective. Alpha will be between 0 and c if the points lie exactly on the margin. So these are the circle points here. So you have three kinds of points. Points that are correctly classified and outside the margin. For them, alpha will be 0. Then you have points that are correctly classified but on the margin. And for those points, alpha will be between 0 and 3. And the third kind of points that are incorrectly classified, those are the ones where alpha equals 3. And so these are statements of facts. If you want to prove this and you are curious in knowing how this works, I have some pointers on the SVM page of the class website. I encourage you to read that. It's actually quite interesting. But so you, in some sense, and so a couple of you already identified the main point here, which is the weight vector W is entirely defined only by points where alpha is not equal to 0, because the weights are simply the linear combination of the input points combined using these alphas. So if alpha equals 0, that point is irrelevant. So the only points that are relevant for defining the weight vector that become relevant at the end of the optimization are points that are on the margin or points that are incorrectly classified. Make sense? Questions? Turns out, now you can get to the question that actually nobody asked this semester. Invariably I have a question. Yes?
So, I mean, does that, I guess, imply that, I guess with this algorithm, that there must necessarily be points on the margin? You can't have like every point like.
You can always find points on the margin, because if I have a collection of points, I can keep zooming in as much as I want. Let's say that there are no points on the margin. Let's pretend that the data set is linearly separable. So the second condition never happens. This one never happens because all points are correctly classified. Let's say that there are no points. You have a hyperplane for which there are no points on the margin. What that means is that you have not grown the margin wide enough. Right? You can keep pushing the margin wide enough till you get points on the margin, and those points define the weight vector. Yes.
So going to an earlier slide where the margin is quadratic.
Yes.
If quadratic or some other nonlinear function.
Sure.
In that case, you will have more support vectors.
I haven't talked about what the word support vector means, so let me just mention that and then we can get your question.
Okay.
Turns out the W, the weight vector, is completely defined only by those examples, those training points whose alphas are not 0. Right? Because if alpha is 0, it does not contribute to this summation. Those training examples which correspond to non-zero values of alpha are called support vectors. And that is why this classifier is called the support vector machine. It's a device that is defined using these support vectors. Turns out, let's get to your question. Who said that this xi here can be linear? I mean, can be the original space, but you could have done some feature transformation as well. You can have support vectors either in the original space or in the blown up feature space. It doesn't matter. There's no, and in fact that observation is what leads to the idea of kernels. So let's work this out. How do you predict? At prediction time, remember that we are predicting using the sign of W transpose X. But we know that the W is equal to this term here, this summation. So let's plug that in. What this means is that by showing that W transpose X is simply, so W transpose X is W transpose the summation alpha I, yi, xi. Sorry. W transpose X is, W is the summation, sum of alpha I, transpose X. Right, for this new example, X that comes in. And here, this summation is over the entire training set. But this is equal to alpha I, yi, xi transpose X. right? I'm just moving the summation, the dot product inside. Okay? So what this means is that in order to make a prediction, I could have maintained this weight vector W, right? I could have maintained the weight vector W and I can take the dot product of W and X. Or I can keep the entire training set in memory, all the Xi, Yi's, and I remember I somehow managed to find all the alphas, and I can compute the prediction by iterating over the entire training set and accumulating this quantity here, alpha Yi, Xi transpose X. So basically taking dot product. So the fundamental operation here now is this dot product. This dot product between a training example and a new example. When a new example comes in, you compute its dot product with all the training examples, the Xi transpose X, and then you multiply by Yi and alpha I, and you add them up. So I could have done the prediction that way as well. Instead of remembering the weight vector, I'm going to now remember the entire training set and all the alphas. A new example comes in, I iterate over the training set. Mathematically equivalent, right? So let's think about this a little bit. The fundamental operation that's needed here is the dot product. The dot product between what? Earlier I said, but I tend to write dot products as transpose. You might ask, sometimes you also see some papers and books writing it in this notation, Xi, X. This is just another way of writing dot product. So all I need to do is compute the dot product between a training example and a new example. But the training example and the new example are both points in this n-dimensional space or d-dimensional space, in the input space. So essentially, in order to build a support vector machine, all I need is a machine that computes dot products between points in the space. Because once I'm able to compute the dot product, I can make a prediction because all I do is compute dot products for the entire training, for the new example with the entire training set. Right? But who said that the inputs should be in the original space? The inputs could have been in the blown up space as well, right? I'm still computing dot products. I could, everything in this analysis would have been true if I just replaced Xi by some feature transformation phi of X. If I transform the features to some space defined by phi, I still need to do the same thing. I need to remember the entire training set, compute the dot product, but now I'm not computing dot products in this original space Xi of the space of X, but I'm computing dot products in this expanded feature space, the transformed feature space. So the whole story repeats. All I need to to implement a support vector machine is this ability to compute dot products in this high dimensional space, in the transformed feature space. Because once I have dot products in the transformed feature space, I can, when a new example comes in, X comes in, I iterate over the entire training set over I, compute dot products between training examples and the new example, but no longer in the original space but in the transformed space. So I compute dot products phi of X, I transpose phi of X. I have a bunch of numbers. Dot products, remember, are just numbers. I have a bunch of numbers. I scale each of them by alpha I, Yi and add them up. I take the sign of that and that gives me a prediction. Nothing changes, right? It's still, who said that if you can compute dot products in the original space, you can compute dot product, if the math works out in the original space, the math works out in the new space as well. So all you need to do is blow up to the new space, compute dot products. Yes?
So how is this different though than I guess what we had before, or I guess with all of the other algorithms where you can just transform your data
That's right.
beforehand?
That's the key point. There's nothing new here. Mathematically they are equivalent. Turns out computationally also they are equivalent. But here's, remember, that, just to kind of, if you've forgotten this slide already, just to remind you, one way of explicitly introducing nonlinearities in your in this setting is to explicitly blow up the feature space. You transform the features using this phi. And what I just showed you now is I can compute dot products. I can compute the prediction of the SVM using only compute dot products in the high dimensional space you know how to use SVMs. We still haven't talked about how to learn these alphas. That, in fact, I'm not even going to talk, we won't see that in the semester. There's reading material, you should check it out. But mathematically, this is true. So, the only operation that matters is the dot product in the high dimensional space. Let's give it a name. Let's call it K. Given two vectors, x and z, I want to compute the dot product of phi of x and phi of z, and let's call it the function k. K is this function that takes x and z and gives you the value of the dot product. Now, the prediction is I've just replaced k here. Right? So the prediction is sine of W transpose phi of x, which is simply the sine of the linear combination of these k's. Okay? Questions about this equivalence? Yes.
So the W here is, since we are doing a dot product with phi x, the W is the...
In the original space. Sorry, in the blown up space.
Right.
Yes. But I'm just moving all the math to the top so that I can put some text at the bottom. If, in order to compute the value of k, I have to explicitly compute phi, and then so let's say that this region of the classroom is the original space and this region is the new space. So a new example comes in, I transform it to the high dimensional space, and then I compute the value of k by actually computing phi. Nothing has changed. We've gained nothing. I mean, it's nice, it's cute mathematically, but we've gained nothing. The interesting bit is, suppose you are able to compute the dot product in the high dimensional space without actually performing the transformation. What if we are able to compute the dot product in a higher dimensional space, but by performing computational operations entirely in the low dimensional space? Wouldn't that be cool? All you have to do is find a dot product in a high dimensional space, and I can tell you how to do it. Transform your point to the high dimensional space, compute the dot product there. The dream here is, can we compute dot products in this high dimensional space by performing operations that are entirely in this low dimensional space? By doing that, we can save some space. Why? Because this high dimensional space might require an array of size million, whereas the low dimensional problem might be an array of size 100. So you don't have to instantiate that array at all. So you save some memory. You can save some time because you don't have to perform operations. You don't have to do this million dimensional dot product. Maybe you can get away by just computing the value of that kernel of that dot product in the lower dimensional space itself. So that might save you time as well. So does the hope make sense? The hope is we want to compute dot product in the high dimensional space, but perform operations only in the low dimensional space. This function k is called, this is the idea of a kernel based method. A kernel is simply a dot product in a higher dimensional space. And I'm going to prove to you by example first that such operations can exist. So in order to do that, let me give you an example of something called a polynomial kernel. In fact, here's an example of a quadratic kernel. Sometimes you'll use instead of feature transformation, you'll see the phrase lifting map. Here's a quadratic lifting map. It lifts examples from the linear space to the quadratic space. How? There are by creating one feature for all various degree terms. So you have all 0 degree terms. That's just a number 1. You have all linear terms, all the x1 through xn. You have all degree 2 terms. You have terms that look like squares and also these products. So there will be, if you have n things here, there will be n choose 2. The dimensionality of phi is n choose 2. Right? It's huge. If you have 1,000 dimensional space, you go to 1,000 square dimensional space. And say I want to compute the dot product, let's call that thing A. A is the dot product of phi of x and phi of z. I can do that. I can transform it and then compute it. Alternatively, I can also compute this other term B, which is the value of k, which is, you take the dot product of these x and z in the original space, add 1 to it and square it. So this is a number, add 1, that's still a number, I can square it. I just get a square of a number. I can compute that, right? You can compute that as well. I have two vectors, I take its dot product, add one, take the square. The cool thing is that A and B are equivalent. The value that they produce will be actually almost equivalent up to some constants. So let me expand on this idea by talking about a particular transformation. Let's say that we have two variables, x1 and x2, and my feature transformation is all linear terms, the degree 0 terms, degree 1 and degree 2 terms. Okay? In fact, let's just have this. Okay, so I have this feature transformation. So let's compute the value of a. So I have x and z. A is phi of x, which is so let's first say phi of x. What's phi of x? x1, x2 square, x2 square, x1, x2. And phi of z is again 1, v1, v2. So what is the value of a? A is 1 plus x1 z1 plus x2 z2 plus x1 square z1 square plus x2 square plus x1 x2 z1 z2. No magic here. I've literally just written out the definition of the dot product of these two vectors. Now let's compute the other thing. So x transpose z is simply x1, the dot product of these two vectors. But this is x1 v1 plus x2 v2. Now 1 plus this is 1, right? What's the square of this? So 1 plus x transpose v square is, I'm going to just write out the square, you can confirm it later if you want, it's 1 plus all the degree, so I'm going to expand the square of this, it's 1 v1 square plus x2 v2 square plus so I'm getting something that looks a lot like this term here, right? Except for the 2. How do you get rid of the 2? I just put a square root 2 here. I can put square root 2's here and here. I think that should give me what I want. Basically, by adding some constants in the feature function, you can basically say that a and b are actually identical. So, what have I proved here? Now, the interesting thing here is, in order to compute the value of a, what has happened? I first had to blow up x to phi of x, I had to blow up z to phi of z, and then compute the dot product. So it requires memory, because you need to store all these things, and it requires time. I need to iterate over this whole thing. Instead of that, I did not blow up anything, I just computed the dot product in the original space. And with this little trick, I was able to compute the value of the dot product in the higher dimensional space. This trick is called the kernel trick. The kernel trick is a computational trick for finding the value of a dot product in a higher dimensional space using operations that are only in the lower dimensional space. What can you do with this? So the advantage of this is now you can do nonlinear SVMs without paying the space penalty, without paying the memory or time penalty of computing dot products. That's why sometimes support vector machines are also called kernel machines. Why? Because they admit the kernel trick. So, sure, I showed you one example of a kernel, but can any function be a kernel? I showed you that this function k is a kernel. What I mean is that this value k, kxz, corresponds to a dot product in some higher dimensional space. Which space? It turns out this space. I've shown you a function k which takes two vectors and produces a number, and the number that it produces is a dot product in some higher dimensional space. Then the natural question is, are all functions kernels? A kernel is simply a function that takes two vectors and produces a number. So tomorrow I am going to invent a new function that takes two vectors and produces a number. Would that be a kernel? It turns out that's not exactly true. Any function cannot be a kernel. A function can be a kernel only if it corresponds to a dot product in the higher dimensional space, right? So only those functions that map to correspond to dot products are higher dimensional spaces. In other words, if you want to prove that your function is a kernel, you need to prove to me that it's a dot product in some space. And there are general ways of doing this. What you do is you construct what's called the gram matrix of that kernel and check that it's positive semi-definite. Let me expand on that a little bit. Just a reminder of positive semi-definite matrices. I'm fairly certain that all of you have seen it at least once, because homework 0 had it. A matrix, a symmetric matrix, is called positive semi-definite if the following condition holds. You take any vector, z, you post-multiply the matrix to that vector and you pre-multiply the matrix to that vector. So you basically ask for z transpose m z, and for any vector, doesn't matter which one. If that quantity is positive, then the matrix is positive semi-definite. It's actually, that quantity is greater than 0. For any vector, if the value of z, for any vector z, if the value of z transpose mz is non-negative, it's greater than 0, then the matrix itself is called positive semi-definite. It's a way of generalizing the idea of positive and negative that we have for numbers to matrices. And positive semi-definite, the idea of positive semi-definiteness of matrices shows up in way too many places, and that I can't enumerate. But it's a very useful idea to have in your toolbox if you want to reason about these things. Now, that's about positive semi-definite matrices. What's the gram matrix? Suppose you have n vectors, and again, I hope that you've seen gram matrices at some point. Suppose you have n vectors, a collection of n vectors, x1 through xn. The gram matrix of this collection is the n by n matrix, whose ijth element is xi transpose xj. So it's simply like this cross product sort of thing. So you get x1 transpose x1, xn transpose xn. And so on. All the other every ijth element is xi transpose xj. That's the matrix. The kernel matrix is the gram matrix of this transformed feature vectors. It's a dot product. What's the kernel matrix? It's basically all the possible dot products. Imagine you have a training set. I can ask for the kernel matrix. It's just the matrix of all possible dot products. It's symmetric, and it's also it turns out the gram matrix is also positive semi-definite. What is the size of this matrix? It does not care about the dimensionality. The matrix is n by n. It does not care about what the underlying dimensionality of these x's are. If the x is 100 dimensional or a million dimensional, the gram matrix will be still n by n, because it's the matrix of all dot products. So with these two ideas, turns out that you can formally define what it means to be a function k. Again, this is a function that has the right signature. This function takes two vectors and produces a number. This function is a kernel if you can show this in two ways. You can show this directly. How do you show it directly? You take the function and you construct a feature vector phi, a feature transformation phi, and show that this function is actually the dot product of this phi x transpose phi z. That's the direct method. And effectively, you're showing that the gram matrix is positive semi-definite for this feature function. Another way of doing this is that you write down the kernel matrix. You write down just the value of, you have a k of x and z, right? You can write down the kernel matrix. which is k x1 z1, k of x1 x1 you have a function k. I can write down this matrix, and you can show that this kernel matrix is a valid kernel by examining this matrix and showing that it's positive semi-definite for any values of x and p. More formally, this is called the Mercer's condition, and kernels are also called, these kernels are called Mercer kernels. Suppose you have a function k which maps any two vectors to a real number, then k is a valid kernel if for any finite set of points, that's important, this condition holds. For any finite set of points, for any values ci and cj, you have the product of ci, cj times k of xi, xj, the sum of all of those things should be positive. This is equivalent to saying if you have vectors c transpose, you have a k, these two are equivalent, and I encourage you to convince yourself they are equivalent. But what the Mercer's condition says is that if you have any finite set of points, x1 through xn, you build the kernel matrix using those finite set of points, that kernel matrix is positive semi-definite. That's the formal statement of what it means for a function to be a kernel. Let's recap where we are. I told you that for support vector machines, you can compute the prediction of the support vector machine only in terms of these operations, only in terms of dot products between the feature mappings. That's point number one. Point number two is the kernel trick. The kernel trick is a computational trick for computing this dot product in the high dimensional space without transforming your points to the high dimensional space. And I showed you an example of the kernel trick for the polynomial kernel. Then I talked about what it means for any function to be a kernel. And for a function k which takes two vectors and produces a number to be a kernel, it is equivalent to saying that this condition holds, the Mercer's condition holds. So this is a theorem that says if a function is a kernel, a function k is a kernel if and only if, for any set of points x1 through xn, you construct the matrix k whose ijth element is the value of k for xi, xj, and that matrix is positive semi-definite. Okay, so let me just probably wind up this lecture. I have 5 minutes. I can actually probably finish this in 5 minutes. I'm going to give you a list of functions that we know are admit this kernel trick, are actually kernels, and I'll also try to show you how to compute the value of the dot product in an efficient way. There's something called the linear kernel. You didn't know this, but everything that we did, all the linear classifiers that we did in the class so far, were the linear kernel. The linear kernel computes the dot products between 2 points x and z in the space itself. It's just saying that the kernel value is the dot product of x and z. A polynomial kernel of degree d is the following feature map. You take 2 points x and z, and the phi here, this case phi of x, is the vector consists of all degree d interactions. So you'll get something like x1 power d, x1 power d minus 1, x2, x1 power d minus 1, x2 and x3 and so on. Basically all degree d terms. For that feature space, you can compute the value of the kernel efficiently by saying you just take the dot product of x and z in the original space and raise that to the power d. That's the kernel trick for degree d polynomials. We've already seen this quad thing here. If I want to compute the dot product, if my feature space is not just all degree d terms, but up to d, so degree 0, 1, 2, 3, up to d, the example that we just saw, I can compute that's called the polynomial kernel that's also called the polynomial kernel, and you can compute that value efficiently by just taking the dot product, adding some constant and raising that thing to the power d. This is a very commonly seen kernel that shows up a lot. It's called the Gaussian kernel, or more popularly, or some people also call it the radial basis function, or the RBF kernel. The value of the RBF kernel is computed in the following way, and this is a kernel function. I'm not going to tell you what the feature lifting map is. I'm going to tell you what the kernel function is. What you do is you get 2 points, you take the distance between those 2 points, that is x and z, you take the distance, it's x minus z square. You scale the distance by some c, and e power minus that quantity is the value of the kernel. First thing to notice is this is a positive number. C is like C is a positive number too, and it's a parameter that you have in the RBF kernel, and this should remind you of the Gaussian function, of the Gaussian distribution. This kernel has the following property: if 2 points are very, very close to each other, think about, first of all, what's a dot product? If you take 2 points and that they are very close to each other, the value of the dot product should be 1, right? If they are unit vectors. Same thing here, if 2 points are very close to each other, this kernel will have a value 1. If 2 points are very far from each other, then, or very dissimilar from each other, then this quantity becomes really big, so you get a large negative quantity in the exponent, so the value of the kernel is close to 0. But as an exercise, I want you to prove to me that this is actually a kernel. How do you prove it? You need to show me that this is a dot product. Or you can use some of the tricks that I'm going to show in the next slide. But what is more interesting is I want you to think about what is the blown up feature space for this kernel. I haven't told you what is the blown up feature space for this kernel. I want you to think about that. How do you construct new kernels? If you give me a kernel function, if you tell me that k is a kernel, or k is a kernel that takes 2 points and produces a number, and it's a valid kernel, it satisfies Mercer's theorem, then if you multiply k by a constant, then it's a valid kernel. If you multiply k by the by some function that is applied to both x and x prime, of x and x prime is a kernel. If you compute the value of the kernel and apply some calculate some polynomial value of it, so you get something like 1 plus k square and so on, that's also a kernel. Exponentiating a kernel gives you a kernel. You can adding 2 kernels gives you a valid kernel. Multiplying 2 kernels gives you a valid kernel. There are also a few other tricks. I'm not going to talk about it, but one interesting thing is if you have a symmetric positive semi-definite matrix, then x transpose ax is also a valid kernel. Okay, I'm going to stop now because I feel like I have a minute and I'm going to I'll take questions.
Could you go back to the polynomial kernel slide? Because it seems like to me that we're choosing phi just to be some arbitrary function. Phi.
Yeah.
But then it seemed like you were saying that we could construct any kernel from the kernel matrix, and so I'm not completely sure how we construct like Kij.
Everything that I'm saying here is that these functions correspond to a particular high dimensional lifting map.
Okay.
We started off this discussion by going from feature maps to kernels. Now I'm saying here are kernels that correspond to certain known feature maps. All I'm saying is these are known kernel functions and they have a kernel trick associated with them.
So we can generate any lifting map from the kernel matrix?
No.
I guess I'm not sure where we're using the kernel matrix.
Where you're using the kernel matrix is only to prove that a function is a kernel.
Okay.
The kernel is just a function that takes 2 vectors and produces a number. And the point of this laundry list here is to show that these are known to be kernels. So here are 2 statements. A kernel is a function that takes 2 vectors and produces a number, but every function that takes 2 vectors and produces a number is not a valid kernel.
Okay.
Because in order to be a valid kernel, it should correspond to a dot product in some higher dimensional space. Everything listed here, these functions are valid kernels, and they correspond to dot products in higher dimensional spaces.
Okay. Good, because I recognize dot product to have like one one definition, you're just multiplying all the elements together.
Right.
But we're defining dot product to mean any function that satisfies the condition you just described.
Yes.
Okay.
Yes. It just so happens that that's a dot product in some higher dimensional space. We don't know, we may not know what the higher dimensional space is. So it's a dot product after performing a feature transformation. It's a dot product exactly the way you recognize it after you perform the feature transformation.
Okay.
But without performing the feature transformation, it may have some weird functional forms, and these two are equivalent.
Okay.
And the whole point of this game is, can we compute the value of the dot product without explicitly doing the feature transformation? Alright, I think I've taken a minute more than I should have, so I'll be happy to take more questions in the office hours.